Welcome to this 22-minute webinar on shop floor programming. Shop Floor Programmer is now included with 3D Experience SolidWorks and SolidWorks Desktop when cloud services are added to the license. In today's session, we'll provide a brief overview of several key apps, giving you a quick glimpse into the enhanced functionality available. Let's dive in by uploading a standard part from SolidWorks into shop floor machining using the 3D Experience platform. We'll begin in SolidWorks with a standard training part and walk through the process of adding the necessary data for use in the shop floor machining app. To get started, we'll save the file within SolidWorks. An important detail to check during the save process is the convert column, which provides feedback confirming that the file has been saved and is ready for downstream use. Once we see the green checkmark, we're ready to add the data into shop floor machining. There are several ways to open the data, but I prefer the simple drag-and-drop method between apps. You'll notice that visible elements, such as sketches in SolidWorks, are also accessible for selection downstream in the machining apps. Switching to the manufacturing cell created upon launching the shop floor machining app, we'll begin by using the wizard on the right. The first step is to import the product we previously opened in SolidWorks. When starting with Shop Floor Programmer, you may not have predefined tools or machines in your workspace. Today, we'll walk through the process of a first-time user setting up a machine and a tool. Once created, these can be reused anytime. In the Generic Machine section, we'll choose a 3-axis machine from the top, assign it a name, and optionally add comments. Next, we'll move on to selecting the post processor. In the Post Processor section, start by selecting ICAM Foundations as the post processor provider. Next, choose either ICAM INCH or from the PP table. Finally, select the HOS post processor and set ISO as the output type. After defining the machine, we'll create the stock material for machining. In this example, we'll keep the stock size identical to the part to demonstrate the process. The final step before programming is to align the part and stock with the part operation and setup. To do this, we match the stock model to the stock selection and the design part to the SolidWorks part. Lastly, we set a clearance plane to ensure tool safety during retraction. Note that in the software, a double-click or pressing escape is used to confirm a selection. As mentioned earlier, we're going through the process as a new user without a pre-built library of machines or tools. In the next step, we'll demonstrate how to create a tool for use in toolpath creation. Remember, once a tool is created, it will be available for use in any other manufacturing cells to program additional parts. Shop floor machining includes tools designed to automate the programming process, one of which is feature recognition. In the next step, we'll demonstrate how to use feature recognition to quickly program 2 outer pockets. This feature can be accessed in the Axial tab. With the feature pre-selected, we can choose the pocket operation and select our previously created tool. From here, we can adjust all standard machining parameters as needed. For this demonstration, we'll accept the default settings to showcase the basic workflow of programming a few features. We'll repeat the process for the similar pocket on the opposite side of the part. The final operation in this example will demonstrate the manual method of selecting geometry. To begin, we'll highlight the pocket operation in the tree and select the pocket operation from the toolbar. Since feature recognition is active, the system waits for us to pick a feature. To bypass this and go directly to the machining operation page, we can press the Escape key. Once on the machining operation page, we'll choose the bottom option and then select the bottom face of the center pocket. Notably, the system includes automation that automatically creates a boundary from the bottom face. Next, we'll select a top face for reference and make a few adjustments to the machining operation. The final step in this process with our sample part is to generate ISO code. To do this, we'll navigate to the Analysis and Output tab and select Generate G-code. Next, we'll assign a name to the container and the file. Once executed, we can review the output using a text editor or a CNC editor. Next, we'll explore the fabrication section of Shop Floor Programmer, which includes nesting, as well as laser, water jet, and plasma cutting capabilities. To begin, we'll upload a job assembly containing 3 parts that need to be cut. The process starts similarly to machining, by saving the flat patterns from Solidworks and dragging them into the shop floor machining app. We'll use the compass in the upper left to navigate to the laser water jet app. In the Setup tab, we'll select Nesting to begin defining key parameters, including the number of components, sheet size, and spacing between parts. We can then preview different nesting outcomes until we achieve the desired results. Once we're satisfied with the nested components, we can follow the same process as before for machine definition, stock selection, component selection, and tool creation. The key difference in this process is that we'll select multiple parts for the design part, and the tool will be defined based on the diameter of the laser beam or water jet. While staying in the Laser and WaterJet app, we'll add a few machining operations to demonstrate the process of programming 2D cutting paths. We'll begin by selecting the cutting head, similar to how we previously selected an end mill. From there, we can utilize automation to select all inside or outside contours for cutting. Using the Manage Contours feature, we can control the cutting order of profiles and apply the same settings to all duplicate components within the nested layout. We'll repeat this process for an outer profile and another part to create multiple machining operations. Once completed, we'll enable the drag and drop function to easily reorder the operations within the tree. The final app we'll explore today is Manufacturing Check. This tool enables users to quickly analyze components and compare designs between additive and traditional machining processes. While there are multiple approaches to building a manufacturing library, today we'll focus on the foundational checks that are available right out of the box. In the Check Processes dialog, we can set standard checks and parameters to evaluate our part. These standards can be predefined in system preferences for future efficiency, but for today, we'll make a few small adjustments to analyze our original Solidworks part. After clicking the check button, we can review the tree on the left to identify features that pass or fail our defined checks. This also provides insights into whether the part is better suited for additive or traditional manufacturing methods. This built-in tool offers engineers a quick validation step, helping them assess their designs before handing them off to manufacturing or production teams. If you have any questions or want to learn more about the apps we covered today, please reach out to your local reseller. Additionally, you can join the Delmia fabrication community through the link in the wizard inside the shop floor machining app. It's a great way to connect with us and other users worldwide. Thank you for joining our session today. Have a great day.